High-speed steel is a subset of tool steels, commonly used in tool bits and cutting tools. It is often used in power saw blades and drill bits. It is superior to the older high-carbon steel tools used extensively through the 1940s in that it can withstand higher temperatures without losing its temper. This property allows HSS to cut faster than high-carbon steel, hence the name high-speed steel. At room temperature, in their generally recommended heat treatment, HSS grades generally display high hardness and abrasion resistance compared with common carbon and tool steels. History: although development of modern high-speed steel began in the second half of the 19th century, there is documented evidence of similar levels of steel produced earlier. These include hardened steels in China in 13th century BC, Wu steel manufactured in India around 350 BC and production of Damascus and Japanese layered steel blades in years 540 AD and 900 AD. High-speed properties of those steels would be mostly coincidental, and the result of local iron ores containing natural traces of tungsten or other favorable alloying components. In 1868 the English metallurgist Robert Forrester Musset developed Musset Steel, considered to be the forerunner of modern high-speed steels. It consisted of 2% carbon, 2.5% manganese, and 7% tungsten. The major advantage of this steel was that it hardened when air-cooled from a temperature at which most steels had to be quenched for hardening. Over the next 30 years the most significant change was the replacement of manganese with chromium. In 1899 and 1900, Frederick Winslow Taylor and Maunsell White, working with a team of assistants at the Bethlehem Steel Company at Bethlehem, Pennsylvania, U.S., performed a series of experiments with the heat treating of existing high-quality tool steels, such as Musset steel. Heating them to much higher temperatures than were typically considered desirable in the industry. Their experiments were characterized by a scientific empiricism in that many different combinations were made and tested, with no regard for conventional wisdom or alchemic recipes, and with detailed records kept of each batch. The end result was a heat treatment process that transformed existing alloys into a new kind of steel that could retain its hardness at higher temperatures, allowing much higher speeds and rate of cutting when machining. The Taylor-White process was patented and created a revolution in the machining industries, in fact necessitating whole new, heavier machine tool designs so the new steel could be used to its full advantage. The patent was hotly contested and eventually nullified. The first alloy that was formally classified as high-speed steel is known by the AISI designation T1, which was introduced in 1910. It was patented by Crucible Steel Company at the beginning of the 20th century. Although molybdenum-rich high-speed steels such as AISI M1 have been used since the 1930s, material shortages and high costs caused by World War II spurred development of less expensive alloys substituting molybdenum for tungsten. The advances in molybdenum-based high-speed steel during this period put them on par with and in certain cases better than tungsten-based high-speed steels. This started with the use of M2 steel instead of T1 steel. Types: high-speed steels are alloys that gain their properties from either tungsten or molybdenum, often with a combination of the two. They belong to the Fe-Ca-X multi-component alloy system where X represents chromium, tungsten, molybdenum, vanadium, or cobalt. Generally, the X component is present in excess of 7%, along with more than 0.60% carbon. The alloying element percentages do not alone bestow the hardness-retaining properties. They also require appropriate high-temperature heat treatment to become true HSS. See history above. In the unified numbering system, tungsten-type grades are assigned numbers in the T120XX series, while molybdenum and intermediate types are T113XX. ASTM standards recognize 7 tungsten types and 17 molybdenum types. The addition of about 10% of tungsten and molybdenum in total maximizes efficiently the hardness and toughness of high-speed steels and maintains those properties at the high temperatures generated when cutting metals. In general, the basic composition of T1HSS is 18% W, 4% Cr, 1% V, 0.7% C and the remainder Fe. Such a HSS tool could machine mild steel at speeds of up to 20 to 30 meters per minute. M2 is molybdenum-based high-speed steel and tungsten molybdenum series. The carbides in it are small and evenly distributed. It has high wear resistance. After heat treatment, its hardness is the same as a T1, but its bending strength can reach 4700 MPa, and its toughness and thermoplasticity are higher than T1 by 50%. It is usually used to manufacture a variety of tools, such as drill bits, taps and reamers. Its decarburization sensitivity is a little bit high. M36 is similar to M2, but with 8% cobalt added. The addition of cobalt increases heat resistance. M36 is also known as HSSE or HSSE. M42 is a molybdenum series high-speed steel alloy with an additional 8% cobalt. It is widely used in metal manufacturing industries because of his superior red hardness as compared to more conventional high-speed steels, allowing for shorter cycle times in production environments due to higher cutting speeds or from the increase in time between tool changes. M42 is also less prone to chipping when used for interrupted cuts and costs less when compared to the same tool made of carbide. Tools made from cobalt-bearing high-speed steels can often be identified by the letters HSS Co. Coatings: to increase the life of high-speed steel, tools are sometimes coated. One such coating is tin. Most coatings generally increase a tool's hardness and/or lubricity. A coating allows the cutting edge of a tool to cleanly pass through the material without having the material gall to it. The coating also helps to decrease the temperature associated with the cutting process and increase the life of the tool. Surface modification: lasers and electron beams can be used as sources of intense heat at the surface for heat treatment, remelting, and compositional modification. It is possible to achieve different molten pool shapes and temperatures. Cooling rates range from 103 to 106 K/1. Beneficially, there is little or no cracking or porosity formation. While the possibilities of heat treating at the surface should be readily apparent, the other applications beg some explanation. At cooling rates in excess of 106 K/1, eutectic microconstituents disappear and there is extreme segregation of substitutional alloying elements. This has the effect of providing the benefits of a glazed part without the associated run-in wear damage. The alloy composition of a part or tool can also be changed to form a high-speed steel on the surface of a lean alloy or to form an alloy or carbide-enriched layer on the surface of a high-speed steel part. Several methods can be used such as foils, pack boronizing, plasma spray powders, powder cord strips, inert gas blow feeders, etc. Although this method has been reported to be both beneficial and stable, it has yet to see widespread commercial use. Applications: the main use of high-speed steels continues to be in the manufacture of various cutting tools, drills, taps, milling cutters, tool bits, gear cutters, saw blades, planer and jointer blades, router bits, etc., although usage for punches and dies is increasing. High-speed steels also found markets in fine hand tools where their relatively good toughness at high hardness, coupled with high abrasion resistance, made them suitable for low-speed applications requiring a durable keen edge, such as files, chisels, hand-plane blades, and high-quality kitchen, pocket knives, and swords. High-speed steel tools are the most popular for use in wood turning, as the speed of movement of the work past the edge is relatively high for handheld tools, and HSS holds its edge far longer than high-carbon steel tools can. See also, Crucible Industries, List of steel producers, references. External links, Effects of elements on steel, a comparison table of different high-speed steel grade standards.